The idea is to discuss a new approach that we have to make predictions about what happened in the first fraction of a second of the Big Bang. And hopefully it will become clear what this approach is. Okay, so this is the standard way that we think about computing things, about the very early universe. In fact, somehow the structure of this will be familiar from other fields of physics, such as particle physics, and so on. So we have something that we observe, and we want to get something out that we predict. Okay, that's the basic structure. In the particular context of cosmology that I want to set up right away, so that we have, the terms around, we are here and we are looking back in time. So this is the arrow of time is going vertical, and this line here represents late time, from which we're looking back towards the first fraction of a second of the Big Bang. And okay, we observe some things and we want to predict others that we have. For example, the one thing that we observed is the two-point function of primordial perturbations. We have measured it very well. So how do we go on from there? Well, the standard approach is to try to write down a model that describes the dynamics during the early universe. So we observe something, the thing we observe, for example, has some symmetries, and then we add to the package some priors that we have, that this is a quantum theory, so it should be unitary. We believe in locality, should be a local theory, and we write down Lagrangians that depend on time, that gives us a story of what happened in that fraction of a second of the Big Bang. And then that's the part that I call model building, and given some model, you can sit down and start your calculations. Usually we do calculations perturbatively, and there's various ways of doing it, and then predictions come out of this. So this is the standard setup, and this is to a large extent how the problem has been approached in the past 20 to 30 years. So what I would like to introduce or describe today is a different way to go about this problem. And the main idea is to go to try to bypass as much as possible, and I think we are successful to a large extent, the model building and the description of anything that happens in time. When I say time, I mean, when I say bulk Lagrangian, I mean as a function of time. But rather, I'll try to go directly from making some assumptions about unitarity, localities, and symmetries, the fundamental principles that are behind the laws of physics, and try to see what I can predict straight away from those assumptions without building a model, and especially without invoking a certain specific time evolution. That's the main idea of the cosmological bootstrap. And hopefully this approach will become clear during the talk, and hopefully it already justifies my title. The story is timeless in the sense that we never invoke any time evolution. We go directly from boundary observables to boundary observables. Okay, I'll start with some motivations to be as broad as possible. Why do I do this? Then I'll try to review for everyone what the main observables are. So that's the important part. And I'll talk about the principles. I mean, you have to set up some principles and study their implications. The principle that will play the biggest role today will be locality, unitarity. And then to make things not too abstract, I'll have a toy example, or actually perhaps not a toy example, we'll say a concrete example, a poster child of how all of these ideas work together and allow us to calculate something which is of phenomenological relevance. And in this case, it will be all possible non-Gaussianities of primordial gravitational waves. There are many things that one can compute with this approach, but to be concrete, I'll focus on that one. And I'll conclude with an outlook. Let me start with some motivations. Okay, this is my one slide of why, if you care about fundamental laws of nature, high energy physics, then you should care about cosmology. At least this is why I care about cosmology. There is much more to cosmology than this, but this is one exciting thing. And it's the idea that thinking about primordial cosmology or measuring, so you go out, take a telescope, look at the sky, and you decide to measure something. It doesn't really matter very much what you measure. It could be matter, dark matter, galaxies, photons, neutrinos, you name it. As long as you're able to measure it on very large distances. As long as these distances are much larger than megaparsecs, then that thing, that product of fluctuations that you have measured, is linearly proportional to the quantum expectation value of the product of fields in the first fraction of the second of a Big Bang. So we have overwhelming evidence for this interpretation. And we know how to go on large scales from the thing you observe to this thing, which is the exciting quantum field theory observable, using some simple transfer function. And so this is why I think it's very exciting to look at cosmological observables, and this gives us an observational tools on quantum field theory correlators, and since there should be also UV completion, some aspects of quantum gravity. And the assumption during this talk would be that the early universe was well approximated by a stage of de Sitter expansion. So for me, this will be quantum field theory correlators around the quasi-de Sitter space-time. So the goal of this talk will be to say as much as possible about these objects. Aspirations. This gives us a handle on many interesting questions in high energy physics. We have already arguably discovered new degrees of freedom beyond those in the standard model, and for sure new energy scales that, as far as we can tell, cannot be made up of standard model constants. For example, the scale at which inflation took place, how long it lasted, and how fast it was slowing down. These are all new objects that we haven't seen in any other aspects of physics except for cosmology. We would like to probe general relativity beyond the regime that we can see at low energies. We would like to, in general, understand quantum field theory in curved space-time. And in Minkowski, we know much more than we do in curved space-time. And de Sitter being a maximally symmetric space, it seems like a good place to start. And more ambitiously, we would like to know about possible UV completions of quantum gravity. We have some good candidates in Minkowski and in ADS. Do they, such as string theory and holography, do they make sense in de Sitter? And can they help us making a more precise prediction for the early universe? So this is the aspirations. I will not answer all of those questions during this talk, but this is where this is going. Okay, so far so good. The approach we've taken so far was initially successful, but we are facing some harder and harder problems to overcome. The main problem is that we have way too many models of the early universe, and we are not able to distinguish among them, given the data, or given any conceivable future data. And really, if you try to find the root cause of the problem, is that no one was there during the early universe to observe the time evolution. So if you give me two models of time evolution that end up on the same state of the universe, I have no idea how to tell you which one is better. They just give me the same outcome. More relevant for theoreticians and for theorists is that we also have very little theoretical guidance as to which models are consistent. We have a hard time telling which models in curved space-time in de Sitters, for example, admit unitary, causal, consistent UV completions. We just don't have the rules yet. And even less, we understand aspects of quantum gravity that we understand in other maximally symmetric space-time, such as ADS, but in de Sitter, the problem has been so far elusive. So the idea of the cosmological bootstrap is to try to find a different way to tackle the problem of understanding quantum field theory in curved space-time, and perhaps that will help us resolve or overcome some of these difficulties. And throughout this talk, I'll give you some concrete example, and my concrete example will be focused on non-Gaussianities of scalars and gravitons, just to be concrete.
Can I jump in with a question? And feel free to put me off to later if you're going to talk about it later. So for this kind of motivation, so my intuition is that with the things you're putting in are going to be so very general, like unitarity and locality. If I had done that in flat space, I would have a class of things that includes all possible models. I wouldn't kind of weed out specific models. I just find that I'd have properties that all models share. And so somehow behind this, the motivation of this approach must be that you're thinking that there's so much symmetry in de Sitter space that it's going to cut down your options, I guess, as opposed to coming up with universal things that every model will predict. Is that the motivation?
Yes, exactly. So there are two motivations. One is that definitely the pendulum has swung too much in the direction of we have too many models rather than too few. So cutting down on a large fraction of them is is helpful. And the other aspects to consider is that we will most likely not be able to probe every possible aspect of the early universe because perturbations are so small. So if we look at very simple variables, such as the 3-point functions that kinematically can only depend on 2 variables, that large degeneracy of models will be highly, the large classes of models will be highly degenerate because the observable that we have is so simple. A great example for amplitude is just the three particle amplitude in Minkowski. You can write down as many models as you want, but if you tell me the helicity of the 3 particles, there is only one solution, and I can write it down without ever mentioning quantum field theory, non-perturbatively. Similar here, as long as the observable is simple enough, it might be that symmetries and fundamental principles are so strong and constraining that actually the answer is very simple and limited.
So it's not like you're going to weed out models, because it sounds like every possible model that's been proposed, I'm assuming, is unitary and local, and so you're going to have. So your hope is that you'll find that the options that can be measured are so limited that it doesn't really matter what the model is. But you're not going to be weeding out models because you're going to have predictions that are consistent with all the models that haven't been written down too, that are also unitary and local. Is that is it?
No, I disagree. So there will be 2 aspects of it. There will be some predictions that will be extremely restrictive, and I'll give an explicit example, is the graviton parity-odd 3-point function. But as far as weeding out model, yes, that's also one of the goals. An example, the problem is that all models that have been written down so far are unitary, local, and causal within the effective field theory, but we don't know which one of those admit a UV completion that is equally unitary, causal, and local. In flat space, we have interesting constraints that come from this requirement that go under the name of positivity bounds, in which you use some general principle like unitarity and analyticity to say that certain contribution from the UV must be positive, and therefore certain infrared Wilson coefficients must be positive. We're trying to do the same for cosmology. So in particular, one of the outcomes of this is that if you give me 5 derivative interactions of an inflaton potential, I'll tell you this has to be positive, this has to be bigger than that, and this has to be bigger than this plus that.
I see. So the weeding out is kind of in the same broad category of the positivity kind of arguments you would have had in flat space. Okay, thank you.
Hopefully, we will also implement a numerical bootstrap that will weed out stuff even non-linearly in the positivity that comes from unitarity. But that's something I can comment later on. In the same type of category as we are weeding out models when we do a conformal bootstrap. We just write down all possible CFT data that is incompatible with unitarity. So those are out. Hopefully something like that can be done also for 3-point function cosmological. Great, yeah, thank you very much, Cliff. And do please keep asking, because I think this makes it much more interesting and fun for everyone. Very good, okay, so that's those are the problems. So now I'll try to tell you a little bit about how we are tackling the problem, and the most important thing is that we all have in mind what it is that we are measuring. Okay, we have to really discuss the observable, so this is maybe obvious for some of you, but okay, so I'll assume that in first fraction of a second of the Big Bang was well described by a metric that looks like the Sitter metric with an exponential scale factor. This is the Penrose diagram of the Sitter, and the one that is relevant for cosmology, is this upper triangle, the so-called Poincaré patch. Infinite past is this green line. We're going to assume that in the infinite past, the quantum state of the universe was described by a wave function, which I'm going to call the Bunch-Davies wave function, and that will be my initial state. And the question that I want to ask is what happens through quantum evolution to this state as I observe it in the infinite future. The infinite future here is this surface at constant time, but in the infinite future. And so I want to know what is the wave function of the universe there. Good. And this eta going to 0 conformal boundary, you can think of it as being a proxy for the reheating surface at the end of inflation. If I can tell you what all of my expectation values, all of my correlators are on that surface, then you can give it to your fellow cosmologists and they can make predictions for the distribution of galaxies. Okay, since the wave function will be an important character in this story, let's look at it a little bit more closely. Of course, this is a wave functional, is a functional of all the fields in the system. So in particular, all the standard model fields, the graviton, and all the inflatons that you want to add to your model. So it's really a functional. Phi here is a collective name for all the fields. And I'm gonna wanna write it for convenience as in the exponential of some powers of the fields with coefficients. If I specify all the values of all of these coefficient psi n's, then I tell you what the wave function is. So the goal of the game will be to find ways to constrain and hopefully compute this wave function coefficient psi n's. The rest of the talk will be about this psi n's. This is not usually what we compute in cosmology. Usually we want to compute expectation values, but to some extent, this is the same that we do in particle physics. We compute amplitudes that are not observable, we square them, and we compute cross sections. This is similar. We compute the wave function, and if you want to compute an observable, the expectation value is just the usual integral over all possible phi of psi observable psi, and that gives you the observable. In fact, the wave function is so closely related to correlators that the quadratic part, the psi2, the one with just two fields, is just the inverse of the 2-point function, and the psi3 is just the 3-point function, and so on and so forth. So in perturbation theory, there is a very simple relation between wave function coefficient and observable, which are the correlators. And for technical reason, it will be more convenient to talk about the wave function coefficient than the correlators. Okay, so this is a wave function, so we know from quantum mechanics how to compute it as a path integral. It's a path integral over all possible histories that obey some boundary condition. In my case, it will be the Bunch-Davies in the infinite past, and they asymptote a certain value on the boundary where I'm evaluating the wave function. So if you give me a model, an action in the form of an action, I put it in here, and this defines the wave function. We have a lot of technology to compute path integrals, and sure enough, this can also be written in terms of Feynman diagrams. Given a theory, the theory has some spectrum. That spectrum tells me that states can propagate from 2 points in the bulk or from the bulk to the boundary. Time here is always running vertically. So the future is the dotted line. And the theory is the one that tells you what vertices should appear here. So those are theory dependent, these FAs. G are bulk-to-bulk propagators, and K are bulk-to-boundary propagators. So in principle, to any order you want, you can just sit down and compute this thing. So this could be the end of my talk to some extent. Just to have you see the propagators, if you have never seen them, since as an example in this talk, I'll mostly talk about massless spin 0 and spin 2 degrees of freedom, so gravitons and scalars. These are the ones that we care about in cosmology. They are the only one that survive at late times. Their propagators are pretty simple. In the infinite past, they oscillate like particles, and in the future, they freeze out and become constant. The 2-point functions are also quite simple. They're famously scale invariant, as we measure in the data. And so now, diagram by diagram, if I give you the vertices, which are the interactions, you can compute everything. However, it's not, okay, you can just compute everything. This is not how I will go about. The reason there is a series of reasons. One is that the calculations are quite complicated. You already see that even at 3 level, for every vertex, I have to compute the time integrals because we don't have time translation invariance, and so time integrals are not for free. And also the consequences of symmetry, such as n of fundamental principles, such as locality and unitarity, they're somehow hidden here in the choice of the model, and it's not clear how they survive in the final observable. So I'll try to go about a different way. Before invoking more complicated principles, such as unitarity and locality, it's useful to get started defining what the symmetries of the problem are. So clearly, we're going to start with homogeneity and isotropy, since that's what we observe in our universe. Invariance under translations and rotations. This is well tested to some extent. Actually, primordial perturbations in our universe have an additional symmetry, which is scale invariance. is the fact that the primordial scalar power spectrum scales exactly like 1/k³ up to some percent corrections given by the tilt. In this talk, I will neglect deviation from scale invariance, which can be treated perturbatively. So now we have a fork in the road. Do we want to stick with only the symmetries we observe, or do we want to add more symmetry to make our life easier and to try to get something much more ambitious? I think both are great options. And for this talk, I'll go the way in which I'll stick only to the observed symmetries and no other. And so only to these three symmetries: translation, rotations, and scale invariant. All the theories that I call the theories of this approach boostless, in the sense that I will never assume any boost invariance. However, there is another approach that I want to mention because it has inspired a lot of the work that has been going on in the field, and one could give another 2 talks just on those set of ideas, which is the approach pioneered by Kani-Hamed, Maldacena, Pimentel, Bauman, Joyce, and their collaborators, in which they assume additional symmetries that are not observed in the data, in particular the sitter boost, and they see how much more they can learn from those. For this talk, I will not pursue that direction, but there is a lot of interplay for sure. For example, let me give you an example of what symmetry buys you, and you already know it very well. In fact, from amplitudes, you already know that if I ask you in a Lorentz invariant theory, what is the 3-particle amplitude, is completely fixed non-perturbatively, just by symmetries. The amplitude for 3 scalar is 1. There's nothing else that is compatible with that. Okay, something similar happens in the sitter for observables that are simple enough, like the cubic wave function, the psi3. And Maldacena and Pimentel show that, for example, for 3 gravitons, there are only 2 functions that obey all the symmetries of the sitter. And these are the 2 functions. The details don't matter. There are some function of the kinematics, K1, K2, K3, and here are written in terms of some spinor-elusivity variables, because the expressions are simpler than with polarization tensors. So you see, symmetries are extremely powerful, as you would expect, and because this is a symmetry-based argument, it's non-perturbative. However, if we want to make realistic prediction for realistic model, we have to do better than this, because we know that our universe is not exactly the sitter. The sitter is eternal, and so there is no history and no cosmology. And in particular, the boost that define the sitter, that at short scales reduced to Lorentz boost, are definitely broken in all models of cosmology. And in most models that are of phenomenological interest, the breaking is large. So in general, we would like to say something that does not rely on the sitter boost. Although for more theoretical questions, that's a great starting point. Okay, so for the rest of the talk, I'll assume that all of the correlators that I compute are invariant under translation. So there is conservation of momentum. They are invariant under rotation. So it's only scalar products. And they're invariant under dilations. But there is no notion of conservation of energy and no notion of boost invariance. Okay, so we got away with the symmetry. Symmetries are fun, but let's try to get some more dynamical principles into the game. And the first principle that I wanted to discuss is locality. I discuss it first because it's the one we understand the least, and but it's the one on which we can make most progress. Okay, so what is locality? Well, colloquially, is the fact that what happens here cannot affect what happens very far away. More precisely, you can think of it as the fact that space-like separated observables, space-like separated operators have to commute. And usually in Minkowski, we phrase this in terms of a cluster decomposition, that the expectation values of the product of operators factorizes as 2 expectation values as you move the operators far away from each other in position space. However, there is no cluster decomposition in the sitter, at least not in a way that we understand at the moment. Because of the expansion of the universe, you could have 2 things interact, and then infinity, the end of infinity for each other. Correlation is maintained, and so there is no sense in which the correlator factorizes. To some extent, this is a problem if you want to ask, well, but I only observe at late time, so what is the implications of bulk locality? I believe in bulk locality. How do I see it? I would say that the question is still largely open in the most general setup. But we have an interesting piece of evidence, which is only valid for massless scalars and gravitons. And so far has been tested only at 3 level, but perhaps it's valid beyond that. But for massless scalars and graviton, there is a very simple relation which is implied by locality. In particular, the way we usually impose locality when we write down models is actually manifest locality. We say in the model, the only interactions that I'm going to allow is the product of operators at the same point and their derivatives. So if you have one such theories that have this property is manifestly local in this sense, then all the wave function coefficient that you can compute satisfy this very simple equation. If you write their dependence on the external momenta, this wave function live in the infinite future. They don't know about time. They only depend on space. They only describe spatial correlation. So they only depend on space, which I can Fourier transform to momenta. If you take the derivative with respect to the norm of the momenta, at 0, those derivatives all have to vanish. Okay, so the Taylor expansion in the norm of the momenta cannot have a linear term. This is simple to prove. It's valid for any 3-level graph. And in practice, it's extremely useful to impose locality. So all theories like effective field theories in which we do write operators of this type, whether they obey boost invariance or not, so you can put dots and spatial derivatives separately, it doesn't matter, as long as they're all local interactions, they will all obey this very simple rule. In particular, gravity itself, gravitational interactions in pure gravity also obey this rule. And this applies to graviton correlators to all orders. There are some cases in which this doesn't apply, but we already know that they cannot give large non-Gaussianities, so we haven't studied it in detail. Okay, there is another beautiful implication of locality, which is the structure of singularity. So since the 60s and perhaps even earlier, we have learned that knowing something about the analytic structure of an observable can be very powerful, and much of the analytic structure is dictated by the singularities if you have some underlying analyticity. So what are the singularities of these objects that we're trying to compute? What is the equivalent of the poles when we compute amplitudes? Okay, so for local theories, this is the structure of singularities at 3 levels. It's well established by now. There can only be one type of singularity. It is when the sum of some, when I say energy, I mean norm of the momenta. When the sum of some energies goes to 0. If you take the sum of all the energy of external fields, I'm going to call that a total energy singularity. It's the sum of all the external ones. Instead, you can also take a sub-diagram and you look at all the energy that is entering that sub-diagram. Also, when that goes to 0, you can have a singularity. The claim is that no other singularities can arise at 3 level. These are the only ones. The residues of the singularities, so this is a consequence of locality. If you break locality, this is gone. So to some extent, this is how locality manifests itself on the boundary, where time has disappeared. The residues of those singularities are fixed by interesting principles. The total energy singularity is actually the flat space amplitude, really the one in Minkowski, in the UV limit, which is a beautiful connection between the sky and particle physics experiments. There are other residues, the residues of partial energy singularities, and those are completely fixed by unitarity, and as I will discuss later. So these are all the singularities that can appear. So,
is there a question there? If not, I have a question.
Okay, yes, please.
So you said that the singularity statement is a consequence of locality, but you said that there were several notions of locality. One was the manifest locality, one was the, I can't remember what you called it, but there was something involving differentiating the wave function with respect to k. Which of them is the one that implies this statement about singularities, that these are the only possible ones?
Yes, so this is really manifest locality, strictly speaking. In fact, it's two assumptions, if we want to be fully explicit. One is an assumption that I stated earlier on, which is that the initial state is bunch-Davis. If that's not the case, if there is any excited initial state that is not bunch-Davis, this is not true. So that's the first important assumption. And I can give you explicit examples in which different singularities emerge. And the second is manifest locality, the fact that the only interactions are derivatives of operators at the same point.
Okay, thank you.
Yeah, that's important. Thanks. Some other questions? So since this is a series of talks about effective field theories, I thought I would make some comments on this, because I don't think that I mean, it is notoriously the effective field theory time-dependent evolution, and they're taking curve space-time, and there are many aspects for which they're taking. I wanted to mention a few facts that are a bit different when we think about effective field theories in this context that we don't see. So first of all, I mean, in effective field theory, we think of expanding an unknown complicated object that depends on UV physics in terms of low energy local operators. So what happens to that expansion? Clearly, if we try to describe the bulk of the evolution, the bulk Lagrangian that evolves the universe, we could try to make such an effective field theory expansion. But if we stick to talking only about the observables at future infinity, what is the consequence there of what is the effective field theory expansion on the boundary, on the thing that we actually observe? So I don't know that I don't think that the answer is completely understood, but I'm gonna make a few comments and a few remarks and perhaps give some hints. The first hint is that the singularities, they are simple, they're poles, but they're not simple poles, they're poles of order P. So in this, I show you P. I didn't tell you what P is. P is actually fixed simply by scaling and dimensional analysis. For example, for our ongoing toy model of a massless scalar field or a graviton, which is what's relevant for observations, this P is given by 1 plus the sum of the dimension of all operators involved in these interactions minus 4. Okay, right here you can see that this starts smelling like an effective field theory expansion. Larger P's come from larger dimension operator. So there is a way in which operators with higher and higher dimensions organize themselves, and they come with bigger and bigger poles, with higher and higher orders in the pole. So just schematically, if you have an interactions of dimension n with delta minus n derivatives and n fields with the right coupling constant for dimensions, to the logarithm of the wave function, this gives you a correction of this size. It's dimensionless, so we can really look at it. It has a term that depends on the coupling constant, and as you would expect, the power is delta minus 4 in this simplest of using the interaction only once. And then it has a kinematic term. Let me discuss first the first one. The first one is interesting. When we talk about effective field theories for amplitudes or in flat space, we have an idea that kinematics give us a way to probe the effective field theories at different energies, right? You crank up your particle accelerator, you're probing an energy which is growing, and then E over lambda, you can make it smaller and smaller and probe high energy physics. This is not what happens in cosmology. The way lambda appears, the way heavy physics decouple, is h over lambda to some power. So the only way, so in cosmology, you might think, well, let me look in the sky at like triangles or momenta of different size, maybe smaller triangles, probe higher energy physics than bigger triangles. That's not the case. Okay, all triangles or all polygons in the momenta, they all probe the same energy scale, which is h over lambda. This is a consequence of the isometries of the sitter, or if you want to, some underlying conformal symmetry. So the only way that you have to probe higher energy is just you build a new universe with a different value of Hubble, of cosmology, of Hubble, and then a different de Sitter, and then you do the experiment again. That's the first comment. The second comment is this, that this is where you see the EFT derivative expansion. Now it appears as an expansion in some polynomial in the kinematics over the pole to some higher and higher power. it would be nice to have a systematic understanding of this feature. I'll leave it at that. It's a long talk to get through. Okay, so it seems that I've told you relatively little, and then it doesn't seem to be practical. So let me show you how to use it to compute something which people have been computing for the past 20 years in a completely different way. Let's say that I want to compute the 3-point function of a scalar field. This is, in fact, the leading observable in all cosmological observations. Every time people talk about the CMB or the galaxies, and they look for primordial signature, they look for a 3-point function of a massless scalar. That's the only one that's given. So how can we compute the 3-point function? I haven't told you how to compute. Okay, here how you compute. You have to set up some rules. The rules are the following. First of all, if we want to compute a 3-level in the system, the result, in my case, the cubic wave function, has to be a rational function. It can be proven that this function is rational also for gravity in every even space-time dimension, so it's not a very restrictive assumption. When you say it's a rational function, well, it's a polynomial divided by a polynomial, but I told you already that locality plus Bunch-Davies imply that the denominator can only be total energy to some pole. The 3-point function is too simple. At 3-level, there is no partial energy. There is only total energy, K1 plus K2 plus K3. Okay, that's the only thing that can appear at the denominator. So then there is very little that this function can be. It can only be a polynomial, and the degree of the polynomial at the numerator is fully fixed by scale invariance. So if you tell me the coefficient, which has numbers in that polynomial, that's it. I'm done with the calculation. And in fact, those numbers can be fixed by the manifestly local test that I told you before. So by requiring that the derivative of that vanishes in 0. So you write down the most generic polynomial, it has a pole, and then in the polynomial, you have some numerical coefficients that multiply the kinematic variables. Sorry, I didn't tell you. E2 and E3 are just products of K1, K2, K3 that are symmetric, so they are most convenient to work with. But if you want, you can write it in terms of K1, K2, K3. And then the only thing you have to tell me is what these free numerical coefficients are. And I claim that all the solutions of these simple equations give you all possible 3-point functions that you could compute in all possible local effective field theories. In fact, we have done it, and we have written down the solution to all orders. It's pretty simple. I'll show you some results. And we have counted how many solutions we have. And then we counted how many independence operators there are in a Lagrangian. And that's tricky because operators want to look like each other. They're field redefinitions away. They're total derivatives away. But if you count them carefully, the number exactly match. So this is a completely different way to compute an observable, a 3-point function, without writing down a bulk Lagrangian and doing the calculation within the bulk Lagrangian, which is much more complicated. It just follows from this relation.
Yes. Just to follow up on that counting. So when you describe the counting and getting rid of redundant operators, I'm thinking that you'll be working to some fixed number of derivatives. But it sounds like you're not making, your statement here is that really this is a general, you've only got so many independent parameters without making some sort of a low energy expansion, it sounds like, right?
Oh, no, sorry. This is true for any number of derivatives, but finite. So you want 273 derivatives. We count it up to that number. We count up to that finite number.
I see.
And they match. But we have the solution we have it is a functional form of a function of n, and is valid for any n.
Okay, thank you.
Yeah. So it's strictly in the EFT expansion. And this is nice because this already basically accounts for most of the things that have been searched for in the data. So this is really, we're doing phenomenology now. For example, if you look at the 0th order solution, that is the famous local non-Gaussianity with some running correction. At first order, when P is 1, there is no solution. This is just the fact that there is no operators that have only one derivative. The only one would be phi dot phi squared with 3 phi's, but that's a total derivative. And then the solution when P is 2 is 3 are the famous local and equilateral non-Gaussianities that have already been computed. So we're just reproducing known results. But all the other ones from P equals 4 onward, they had never been computed, and they easily follow from this discussion. Of course, they are higher dimension operators, but it's nice to know what they look like. And here is just a plot. If you want to search for them in the Galaxy 3-point function, this is what they look like. Much more could be said about this, but I'll try to keep it short. Okay, so the next topic is, so far it seems that unitarity didn't play much of a role, although this is just because we're looking at something very simple, but definitely if we are writing down a quantum theory, we have to be sure that the probabilities we compute from it are between 0 and 1. And so that's where unitarity comes into place. To ensure that that probability is 0 and 1, we're going to consider the case in which time evolution is unitary. So u dagger equals 1. And we're going to ask, what are the consequences of this? If I assume I have some Hermitian Hamiltonian that gives me unitary evolution, and I start with some Bunch-Davies state, is there something about the final wave function of the universe that looks particular? Are there any consequences? Does anything goes, or is there any remnant, any notion of unitarity? Notice that it's not obvious, because the final observable that I'm talking about is the wave function at late time that does not depend on time. It's not obvious how time evolution will be encoded there, but of course we know it should be there somewhere, probably on the complex plane. And in fact, for amplitudes, we have known for 6 years, perhaps even more years, the consequence of unitarity. Of course, it's the optical theorem, and then in perturbation theory, those are Katkowski cutting rules. So what's the equivalent in cosmology? And this was not known until just a couple of years ago, remarkably, despite it being a relatively simple question. So let me tell you what the consequences of UU dagger are. And there are infinitely many consequences to increasing order in perturbation theory, as you would expect. Let's consider the simplest possible interaction, just a single interactions with n fields. They interact once, and then they go their merry way to the boundary. Then I claim that for that case, if you compute the wave function as function of the energies and of the scalar products of k1 dot k2, etc., plus the wave function itself with a star, and you put a minus on all the energies and all the momenta. Okay, that's a funny thing to do because the norm of a vector is positive, but so what's funny is that you put a minus, but that's the statement. If you do this analytic continuation, that's 0 for all possible interactions. This is how unitarity emerges in this simple context. Since this particular combination of psi plus psi star of minus k comes up all the time, all over the place, it's useful to give it a quicker name. I'm going to call it the discontinuity of psi. Is this very specific relation, psi of k plus psi star of minus k. Okay, equipped with that piece of notation, I can give you what the consequences of unitarity are to all orders in perturbation, any number of loops. Let's look at this next simplest graph, 4-point function. The discontinuity of this, keeping the internal momentum fixed, is equal to all possible ways to cut internal lines. There is only one, so only one way. When you cut it, it means that you push the internal lines to the boundary. So instead of being an exchange, it becomes two boundary. This divides the 4-point function into two 3-point functions, and then you take the discontinuity of each one of them, and you put the power spectrum because you have cut the line. This is exactly what you expect from unitarity in perturbation theory. It's a nonlinear relation that relates lower order stuff to higher order stuff, which is why it's useful. This actually works, and we proved it in full generality for all diagrams to all orders to any number of loops. So this also works for loops, it's not specific. And perhaps what's important to capture is that it works for any field of any mass, any spin, arbitrary interactions in any FLRW space-time, as long as you enforce a Bunch-Davies initial state. This has nothing to do with de Sitter. So it's an extremely powerful set of relations that we can use to learn, to simplify our calculations, and in some cases to fully constrain the final result without even doing the calculation. I'll give you a few examples. There is an example that I will not discuss very much, but that's perhaps one of the strongest use of unitarity in particle physics, is to compute loop diagrams through their cuts. Something similar, this unitarity methods for loop amplitudes. This can be done here as well. And in fact, we computed the one loop corrections to the power spectrum in the effective field theory of inflation, of which only one term was known in the literature before. But with this approach, you see, the discontinuity of this one loop diagram is fully fixed by 3-level diagrams, because when you cut it, this is not a loop anymore. It's 3-level, 3-level, 3-level. And we know all those 3-level diagrams already. So the calculation is particularly simple. It would be nice to explore this much more, but I don't have time here. Okay, so I'm gonna move on from stating unitarity to using unitarity. So this is a good time to complain about something if you have some complaints.
Not a complaint, but so in the previous thing, this discontinuity is a statement that all the observables you want to track can be given in terms of the discontinuity, or is there a way of getting the whole answer from the discontinuity?
Great question. I don't think this has been proven or explored to any extent of generality. What I can tell you is that at 3-level, this is definitely fixing the full answer up to contact terms that have no discontinuity. So that's some kind of equivalent statement. So for example, a 4-point function, I can fix it up to a contact interactions because that has a 0 discontinuity. And so it's compatible with any discontinuity that I can determine. And there are two ways to do that. One is using some so-called partial energy recursion relation. You do a complex shift in energy, which picks up all the poles, and the poles are fixed by this, similar to BCFW recursion relation. And that's something we developed. And then there's another beautiful formula by David Meltzer, in which he writes the full object in a dispersive way, as an integral of the discontinuity. And that fixes it, but always up to a contact. The contact has 0 discontinuity, so you can never fix that. It's the equivalent of what would be the boundary term in BCFW. If you have theories in which there is no boundary term, then you can fix the full thing. But generic theories do have this extra terms that are allowed.
Okay. All right. Thank you.
So that's an excellent question. And at the loop level, actually, no one has really investigated what theories are loop constructible. In amplitude, there is this concept of loop constructible, where the full loop is defined just by its cuts. I give you all the cuts, and then there is no other answer compatible with that. It would be nice to know which theories are loop constructible in this sense in cosmology. We are far from achieving that. But maybe someone in the audience that know much more than I do about unitarity methods could approach the problem. Okay, let me give you another example of how to use unitarity, which I think is very neat. I think it's neat. I think it should be the poster child of this. Okay, so we want to compute correlators eventually. That's the observable. And so we have to put the thing inside the integral and do the integral with psi star. That's how we compute expectation values in quantum mechanics. So when you do it to linear order for the simplest contributions, you take this psi, it's an exponential, you bring down an interaction. When it comes from psi, is a psi n. When it comes from psi star, is a psi n star. Okay, so this is what a contact correlator looks like a 3-point function. All of them looks like that. Now you see this particular combination that appears here is very similar to the discontinuity I just told you, except that there is no minus in front of the energy. So automatically you know that if the wave function you're looking at is even when the energy gets a minus, for example, it's case like k squared, well, then this numerator is 0. And you already know that that thing can never give you a correlator. Okay, so we already see that a lot of correlators are going to be highly constrained by unitarity in this sense. So let's see how that works. First, I'm going to show you something in which is not very constrained. So the simplest case is parity-even interactions of, for example, 3 gravitons. Okay, you can have parity-even interactions. There is an even number of derivatives. And then I already told you that the wave function should be a polynomial over kt to some pole. And there are additional terms that I haven't discussed very much. They correspond to IR divergences. Then if you have 2 derivatives, then there is a k square, and then you have to reduce the order of all of these polynomials by 2, because now you have paid 2 derivatives, so the order is less. Now we can go around and see which one of these are compatible with are going to set to 0 by unitarity when we compute a correlator. Well, this is okay, so this is odd, so it can survive. This is odd, so it can survive. And this is odd, so it can survive. So we find that for parity-even correlators, we have infinitely many, all possible polynomials of degree 3 plus p divided by kt to the p. And also at two derivative levels, we have infinitely many. Okay, so that's interesting. We expect infinitely many. That's perhaps not so surprising. We have a derivative expansion. There are infinitely many interactions. And so there are infinitely many operators that can contribute. But see what happens when we go to parity odd. Now we have an odd number of spatial derivatives in front. To be parity odd, there's just one derivative contracted with epsilon or three derivatives contracted with epsilon. Then then the order of this polynomial has to be decreased by 1. So now this function is an even function in K. It's not odd anymore. So it cannot contribute to the correlator. When you put it in the correlator, it exactly cancels because of unitarity. So this cannot lead to a correlator, neither this, neither this, neither that. So most terms will disappear. This term actually cannot because of locality. So pretty much everything has disappeared because of unitarity. The only term that survived is this I pi over 2 here, which comes with a quadratic polynomial, but has an I, and so it is saved. But notice that all the terms that had poles have disappeared. Those were the infinitely many terms. The only term that survives is just a second order polynomial. And so there are only very few second order polynomials I can write down that are linearly independent. And so there should be only a handful of 3-point functions, parity-odd of gravitons. And they cannot have KT poles. That's quite remarkable. So let me show you the result. So let's say that you want to compute the 3-point function of a graviton with plus, plus, plus. It has a 3 polarization tensors contracted with momenta, and then some function. This function is the one that satisfies the manifestly local test. And this one in front can be neatly written in terms of spin-or-helicity variables, as I have done here. If you don't know about that or cannot follow from this slide, it doesn't matter. It's something which is semi-standard. You just capture the little group scaling of this object, and you make up for what's not in the spin-or-helicity, but it's in the polarization by adding these H polynomials, which can be written down just by explicitly writing down all possible cases, as we have done. So the only unknown part of this cubic wave function is this polynomial. But I just told you that this cannot have poles. It's only polynomials in K1, K2, K3 of second order, and it should satisfy locality. Okay, let's try to contrast this with what our expectations are. If I ask you what is the 3-point function of 3 gravitons, you would tell me probably there are infinitely many of them. I can certainly write down 3 Riemann or 32 Riemanns and contract them with an epsilon. That's parity odd, totally diff invariant, nothing wrong with it, totally unitary. I can definitely expand it to cubic order in the graviton and compute. And every time you compute, you will find one of these 3 answers, which is quite remarkable because you have infinitely many operators, but only 3 possible answers. To some extent, this is not so surprising. Also for the amplitude of 3 scalars, you know that there are infinitely many operators, but they are all related to each other by field redefinitions. Here it's a little bit more subtle, but it's a similar story. The observables, there are only 3 possible things. And these 3s are the one corresponding to these 3 specific polynomials, where this denominator just comes from rescaling wave function to correlators. And this is the polynomial that I told you about. And we computed all those 3 polynomials. So the claim is that to all ordering derivatives, these are the only possible 3-point functions of gravitons that can ever come out that are parity odd. If you compute anything else, you made a mistake in the calculation. I like this example. It's a poster child of the approach because from a Lagrangian, it would have been hard to find this result, and in fact, it wasn't known. None of the shapes was known before, and it wasn't known that there were only 3. The Lagrangian is infinitely degenerate in this case, as far as this observable is concerned. Actually, the same is true if you take two scalars and a graviton, or one scalar and two gravitons. The parity-odd one is also highly constrained. There is only a single scalar-scalar graviton and only three scalar-graviton-graviton with three coupling constants here that are arbitrary. And then the polynomials are fixed. And the overall scaling is just given by the usual spin-or-helicity variables.
Sorry, can I ask a question?
Yes, Barnum.
Yeah, I'm not sure I understood this very well, but I guess you told us that manifest local test doesn't apply for graviton because you have 1 over Laplacian, but now you're using this for computing this, no?
No, I actually did not say that.
Oh, sorry, I'm sorry.
I think no, but it's an excellent point. That I was confused about it a year ago, but I think now I'm clear with it. The manifestly local test, it is true that if there were inverse Laplacians, then the manifestly local test would not work because they're not manifestly local, exactly as you point out. And we know from Maldacena that when you solve constraints for scalar perturbations, you get inverse Laplacians. So if they were to appear, that would be a problem. I claim that in pure gravity, which is only a spin2 degree of freedom, those inverse Laplacians only ever hit 2 or more perturbations. You can never have inverse Laplacian of a field by itself when you solve the constraint. That's obvious because those inverse Laplacian come from solving constraints. The constraints are the lapse and the shift, which is a scalar and a vector, and they cannot be linearly related to a tensor. So that can never appear. So the only thing that can never appear, so we have N and Ni, schematically, they could be gamma plus gamma squared plus gamma cubed plus da, 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 okay? I claim that this can never appear because you cannot mix a scalar with a tensor or a vector. So this can only appear. But then this, although it is not manifestly local, it still obeys the manifest local test. Because when one mode is soft, this does not lead to a divergence because the inverse Laplacian is Q1 plus Q2 squared. So when Q1 is soft, this is not a singular. This is the reason. So it does apply to gravity to all orders.
I see.
Pure gravity.
Okay, thanks.
And in fact, we use it to compute the graviton 4-point function, but I don't have time to discuss that in this talk. But thanks, Barna, for pointing this out. It's worth explaining. Great. Yeah. Some other question. Okay. Okay. If not, let me just make, perhaps this is not the interest of this audience, make some more phenomenological thing. These are actually things that people should look for in the sky. Okay, so there's 3 shapes. If we ever are so lucky to see gravitons in the sky, and we start asking if they're primordial and test their non-Gaussianity, this should be some of the primary targets. Yeah. So you can plot them and see what they look like, and people can search for the signal in the CMB, in the B mode, CMB B modes. Okay, so far I never wrote down a model, right? It was all just unitarity, locality, just talking about the observable. So what can I actually obtain this thing from a model? And the answer is yes, as you would expect. In fact, there is a large class of models that they're called solid inflation, and all of the graviton non-Gaussianity. Sorry, I should have mentioned in the paper we also compute all the parity-even non-Gaussianities, but there are infinitely many of those. Okay, so all of the one we compute, you can find a model in which that's generated. Okay, so to some extent we get to the same result if you have written down all possible models and computed all possible graviton 3-point function. You would have found the same class. I would argue with much more effort. In more minimal models like the EFT of inflation, actually the result we're finding, not all of them can arise, but only a specific linear combination of those. So what we're finding is the most generic possibility, and if your model is not the most generic model, then it makes sense that it might not give you all those possible signals. Okay, and if you were to look for that in the sky, you should probably look for two scalars and a tensor. That's the easiest one to see in terms of signal to noise ratio. But I don't think that's perhaps so much the emphasis here. Okay, well, I'm going to be making it just on time, so I'll come to a summary of what I've told you. So I think there has been quite a lot of progress, I mean, in the past few years on understanding primordial perturbations, correlators, and the wave function from a completely different point of view. And all of these things were not known even like 4 years ago. So there is a lot of games that one can play that we haven't tried. And there are many new, very general results that have not been derived yet. I've showed you as an invitation some quite general results, the cosmological optical theorem, for example, as well as some initial consequences of locality, but I hope that much more can be done in that direction. And already those are strong enough that simple observable like 3-point functions of scalars and graviton, which is true that they're very simple, but they're probably the only one that we care about observationally. They are highly constrained by this. And I showed you how you can actually do calculation with this. And I show you that you find surprising results. For example, that there are only 3 parity-odd graviton non-Gaussianities, despite infinitely many Lagrangians. So there is a lot more that can be done, and I hope you appreciate this is really a wide open field. There are some pretty basic questions that people have not understood yet. So there is quite a bit of simple things that can still make an impact. So one, which is what I was mentioning at the beginning, is this idea of positivity bounds. I think on the phenomenological side, as well as theoretical, that's probably the most interesting. How can we weed out effective field theories on the sitter based on them not having consistent UV completions? And I don't think we can do that in Minkowski by taking the Minkowski limit. I think we should really do it in the sitter, so we need to learn how to do it. For that, we need to understand the analytic structures of wave functions as a function of kinematics. And finally, 2 more that I wanted to propose to this audience. I don't know if there's someone who's interested in this. I don't think that the effective field theory expansion is fully understood on the boundary of the sitter. So usually when we do effective field theories, we go to the bulk Lagrangian, time dependence, integrate out modes, and even there are many subtleties. It would be nice to know what is the equivalent. What does separation of scale buys you at the level of observables? How do observables simplify when you have a large separation of scale? So how do you do EFT on the boundary? There is no time. What is the consequence of locality there? I think it's an open question. We have a lot of perturbative calculation in which you can test if you get the right answer. And more generally, if you knew the analytic structure in perturbation theory, we could declare that that's the analytic structure non-perturbatively, and then you can start doing like the CFT bootstrap or the S-matrix bootstrap. You can start computing correlators non-perturbatively. And I think that would be very, very interesting. So I'll stop there, and